Yeah, dear students, welcome to our course Linear Algebra. In this course, first lecture is vector spaces. In this lecture, we are going to discuss what is the vector space and some examples on vector space. We'll see what is the vector space first of a vector space. What that means a vector space V. Vector space generally denoting V. We represent V over a field F. Last class we discussed field. Define a vector space over a field F consists of a set on which two operations. One operation is called vector addition and another operation is called scalar multiplication. This addition operation and multiplication are defined such that the following axioms holds or following conditions holds. First one, it's a closed property. That means it's a binary operation. It's closed. Whatever two vectors u comma v belongs to v, u plus v belongs to v. It's a closed one. First property. Vectors is closed. That means you can say this dot is plus is binary operation. Last class we did, I said what is the binary operation. The closed property means the addition is the binary operation. A second property, for all u comma v comma w belongs to v, three vectors. That means u plus v belong plus w equal to u plus v plus w. This is associative property. Addition is satisfied vector addition property. Now third one, there exists an element in V. Any vector like any element in V denoted by 0 such that u plus 0 equal to u for all u belongs to V. For any vector u plus 0 equal to u. That means 0 is uh, identity. 0 is identity. This is 0 vector is identity. Another fourth one, for all u belongs to V, there exists V belongs to V such that u plus V equal to 0. 0 vector. Here u equal to minus v. This minus v is vector addition. Vector, not vector. Additive inverse. Additive inverse. Additive inverse. A fourth property, commutative property. For all uv belongs to v, u plus v equal to v plus v. Any two elements in v, that u plus v same as v plus v. With respect to addition. A sixth property, for each alpha belongs to f, any alpha belongs to f, v belongs to v. Alpha dot v belongs to v. It's a closed. So closed means that is binary operation. Binary operation here. Closed property is binary operation. Now seventh property, for each v belongs to v, one dot v same as in v. Any vector, if you multiply with one, again it's a vector in v, in vector space. Eighth property, another one, alpha belongs to f. It's a scalar. Sorry, some element of u comma v belongs to v. Alpha dot u plus v equal to alpha dot u plus alpha dot v. This is a distribution law. Alpha dot u plus alpha dot v. Another one. This is a distribution on vectors. This is a distribution on the scalars. This is a left distribution is on vector. This is a right distribution on scalars. For alpha belongs to v, alpha beta belongs to f, u belongs to v. Alpha plus beta dot u equal to this one, distribution property. Yeah, this one. So, the elements of the field f are called scalars. These elements, what is alpha, beta, we are denoting. And f is the field. These field elements are called scalars. The elements of the vector space V are called vectors. Yeah, whatever we have taken u, v, w, these are the vectors in V. Taken in vector space means that's a vector. Elements in vector space is vectors. Generally, we write vector space V over F. We write Vs, vector space V over F. Now observe here one more thing. Alpha dot V belongs to F. Yeah, alpha belongs to field, V belongs to V. That means the scalar product in vector space. That means the field always subset of vector space. The field is always subset of vector space. That vector space is superset of a field. Generally, in this our course, mostly we are taken field is real numbers. Field is mostly we are taking field is real numbers. One more thing, if I, that is, this always vector space is superset. That means we will see if you write R over Q, maybe it's a vector space. Suppose if I write Q over R, it's not a vector space. It's because this property is not satisfied. Closure property with respect to this one. This closure property is not satisfied. Means vector space is always superset of field. Complex number over R, you can write it's a vector space. But R over it's not vector space. This is because here R is the complex numbers are superset. But this is not such this sixth property, closure property. Now remember one thing that vector space is always superset. Starts with these nine properties, then the set is called vector space. We write vector space V over with respect to vector addition and scalar multiplication. Now see some examples. First one, V equal to Rn and taken vector space is Rn space. F is field is R, real numbers. We write Rn over R, vector space and field. Generally we write vector over F, V Rn over R. Here Rn is the vector space, R is the field. For U is U and V belongs to Rn. That these are the vectors. U and V are vectors in Rn. Some alpha belongs to F. It's a scalar. If the vector addition and scalar multiplication are defined as, it's a defined vector addition and scalar multiplication. They're given two conditions. Now you have to show that it's a vector space. That means these two conditions satisfy all nine properties. All we define that vector space. It satisfies these nine conditions. Now check that one. First property. That's the closure property. For U comma V belongs to Rn. Rn is the vector space. This is the vector space. Rn. Closure property means U plus V equal to closure property. UV belongs to R vector space. U plus V belongs to vector space. Now check this one. U plus V. What the U means? It's defined. Given UV. U equal to A1, A2, A. Plus V is B1, B2, Bn. Now it belongs to Rn. Already we discussed last I explained in introduction class. Whenever we take vector space, suppose we have taken order pair. Suppose V1, V2 in R2. Here V1, V2 belongs to V1, V2 belongs to real numbers. That's one line. Here also U, V belongs to Rn. A1, A2, An, B1, B2, Bn are real numbers. Here that means the real numbers satisfy closure property. Already we know this real numbers are field closure property. One more thing in this one, whenever it satisfies this 5 condition up to 5 elements, then that V plus is called a Abelian group or commutative group. Abelian group, or you can say commutative group. It satisfies these 5 conditions. Closure property and associative and identity exist and inverse exist and commutative. It's a Abelian group. The real numbers always Abelian group. Yeah, now this one it satisfies closure property. That means A1 plus B1, A2 plus B2, and so on, An plus Bn. So now A1, B1 real number, A1 plus B1, that addition also is closure property means it's also a real number. That means it belongs to Rn. These all elements in real numbers. Rn. Therefore, dot is this is closed. First condition is satisfied. Addition is closed. Next, take for U, V, W belongs to Rn. Take W is vector in Rn means take W equal to from C1, C2, Cn. Verify it satisfies associative property. Now take U plus V plus W is equal to U plus U means now first write V plus W. V equal to B1, B2 and Bn plus W equal to C1, C2, Cn. A1, A2, An plus this one B1, B2, this addition property because these elements are real numbers B1, B2, Bn, C1. This also that closure property that means B1 plus C1, B2 plus C2 and so on Bn plus Cn. Now this is equal to again it's a real numbers. Again it satisfies closure property. That's why we can write A1 plus B1 plus C1, comma A2 plus B2 plus C2, comma and so on An plus Bn plus Cn. So now this is the real numbers. Real numbers are the associative property. This one can I write? This one can I write? A1 plus B1 plus C1 because real numbers are also associative property. Similar this one. A1 plus B1 plus C1 writing A1 plus B1 plus C1. Next A2 plus B2 plus C2 and so on An plus Bn plus Cn. This is equal to this is A1 plus B1. This is same as you can write reverse. That means this is you get U plus V plus W. That means it starts with associative property. Therefore, associative property, associative hold. The second condition, associative hold. U plus V plus W same as the U plus V plus W. Next, third one, identity. For U belongs to Rn, take 0 vector. And U also vector, I'm not writing in this arrow mark. Yeah, whatever you take in vector space element is always vectors. Belongs to Rn. Now, U plus 0. U is A1, A2, and so on A plus 0 vector. 0 vector in Rn, not R2. Rn means already last class I told you. The element in Rn means it's n tuples. 0 also has n tuples. That 0, 0, 0. That is closure property. That's A1 plus 0, A2 plus 0, and so on An plus 0. Yeah, A1 plus 0. These are real numbers. A1 plus 0, that A1 only. Is equal to A1, A2, A. That equal to U. Similarly, you can prove 0 plus U equal to U. Yeah, therefore, 0 vector is identity. You can say identity or vector identity. Fourth property. Take U plus minus U. The minus means negative vector. Or the U means A1, A2, An plus minus means minus A1, minus A2, minus A. minus v means minus a vector, negative vector. Minus of u equal to minus this one. Okay. Negative vector. This is a real elements. That one you can write a1 minus a1 addition. Okay, right. Plus of minus a1, a2 plus minus of a2, and so on. An plus minus of an. See, a1 minus of a1, that is 0. 0. A2 minus of 0, and so on. 0. It is 0 vector is equal to 0 vector. U plus minus of u equal to 0 vector. Therefore, minus u is additive inverse. Additive inverse. Fourth one. Next to fifth property. For u comma v belongs to Rn, u plus v equal to. What is u plus v equal to? A1, A2, An plus B1 plus B1, B2, Bn. This is equal to that is closure property. This one you can write A1 plus B1, A2 plus B2, so on, N plus N. This is equal to, so these are real numbers. The real numbers satisfy commutative property. This one you can write B1 plus A1, B2 plus A2, and so on, Bn plus N. This is equal to B1, U plus V equal to A1 B1. This one you can get V plus U. That means V plus W is abelian group. It's commutative property. That's the five condition, abelian group. Abelian group. Okay. When you try this abelian group. Now remaining four properties. That's why vector addition property. Now scalar multiplication properties. Sixth one, for alpha belongs to F. F is the real number here. It's a field already. And U belongs to Rn. So now, what about alpha dot U? Alpha dot U must be in vector space. Now you can check it. This alpha dot U. U means A1, A2, A. Is equal to alpha A1, alpha A2, alpha A. So now observe here, alpha is a real number. This A1, A2, An also real number. That means alpha real number A1. This is a real number. This all are real number. Alpha A2, alpha N. This all are real number. This N2 pulls. It belongs to Rn. It means it's a vector space. That means therefore dot is closed. Therefore dot is closed. The scalar multiplication is closed. Now seventh property, for U belongs to Rn. What about 1 dot Rn? 1 dot U. 1 dot U must be U. Now 1 dot, that means you can write 1 dot A1, A2, A. The same as 1 dot A1, 1 dot A2, 1 dot A. 1 dot A1 same as the A1. This A1, A2, A. That is equal to U. This is seventh property. Now eighth property, that is distribution. For alpha belongs to U field, and U comma V belongs to R. And then now left distribution, alpha dot U plus V is equal to alpha dot U plus V. Alpha dot, already you know U plus V, can I write directly? This is A1 plus B1, A2 plus B2, comma, up to so on, N plus Bn. Alpha is a variable, these all are real number. We know real numbers are satisfied distribution property. So we can write now, no, not distribution, but scalar multiplication. scalar multiplication. Alpha dot u. This we can write alpha dot a1 plus b1, alpha dot a2 plus b2, and so on. Alpha dot an plus bn. These all are real number. It starts by distribution property. That one you can write alpha dot a1 plus alpha dot b2, comma alpha dot a2 plus alpha dot b2, and so on. Alpha dot an plus alpha dot bn. This one can write alpha dot a1 comma alpha dot b1, alpha dot a1, alpha dot a2, and so on. Alpha dot an plus alpha dot b1, alpha dot b2, and so on. Alpha dot bn. That means that alpha dot a1, alpha dot this alpha dot. Again, you can take common alpha this a1 because it starts to close out a2 a plus alpha into b1 b2 bn. The same as alpha dot u drink alpha dot u plus alpha dot v. That's all. Distribution loss. Next to last property, for alpha comma beta belongs to field and u belongs to Rn. Whatever it's alpha plus beta dot u. You can this one alpha dot now u means u1 u2. This one correct u1 a1 plus alpha plus b dot into a2 and so on. I'm writing directly. So alpha plus beta dot a dot. Simple for this one. It starts. These are real numbers. Again, you can apply distribution laws. So apply and simplification will get this is alpha dot u plus alpha beta dot u. It starts by write a distribution on scalars. This is a distribution on vectors. Starts all 9 properties. Therefore, V over F, that is Rn over R, is a vector space. Vs vector space. That means it's also 9 properties. Vector addition is 5 properties and scalar multiplication is 4 properties. If it also all 9 properties, then the set is called vector space over some field. This one. I will see another example. The set of all real polynomials of degree less than or equal to n, less than or equal to n, over the real field. The real field means real numbers. Under the usual vector addition and scalar multiplication of polynomials is a vector space. The solution, just I give idea, you can verify this all 9 properties. Now we have taken real polynomials of degree less than or equal to n. And where vector space is polynomial, P of n. Generally we denoting Pn means polynomial with whose degree less than or equal to n. And field is the R. Let's take polynomial. Let Pn, small pn. This is a capital P. This is capital P, right? Set of all the polynomial. Let P1 a0 plus a1x plus a2x square and so on. En x power n, whose degree less than or equal to n, must be less than or equal to n, and Qn equal to Pn and Qn. Now some b0 plus b1x plus b2x square and so on. Bn xn belongs to vector space V, that is Pn. Vector space. Now take this one. Now you have to verify vector addition and scalar multiplication. Now you have to verify just Pn plus Qn. That is usually vector addition and scalar multiplication. But how to apply Pn Qn? When you write Pn Qn, a naught plus a1x plus and so on, a naught x power n plus b naught plus b1x plus bnx power n. How to add two polynomials? This is a naught plus b naught plus a1 plus b1x plus and so on, an plus bnx power n. It's again polynomial. This is with coefficients. This a0, a1, these are real numbers. A0, b0 real number, a0 plus b0 are again real number. This a1, b1 also real number. It belongs to vector space. That means dot is closed. Now check associative property. Associative property, take Pn plus Qn. Take another PQR, some Rn polynomial. Take Rn equal to some C0 plus C1x plus and so on, Cnxn. Rn polynomial. Now verify associative property. This one same as you can write Pn plus Rn. Associative property. And identity. Zero polynomial. Take zero polynomial. What is the zero polynomial? Zero polynomial, you can write 0 plus 0 dot x plus 0 dot x square and so on, 0 dot x power n. Zero polynomial is there. So this is the identity in a vector space, in the polynomial vector space. This one. Now identity. Zero polynomial is the identity. Now take Pn and minus Pn plus minus Pn. If you take this, will get Pn minus Pn. When you are adding Pn minus Pn, we get zero polynomial. Zero polynomial. That means minus Pn is the additive inverse. Next one. Next another property, commutative. You can check commutative usually. You can write Pn plus Qn is same as the Pn plus Pn. Because Pn Qn, we get a0 b0. This a0 b is real numbers. Real numbers is such a commutative property. That means you can write b0 plus a0. Similarly, b1 plus a1. Same as the Qn plus Pn will get. This is the one. Next, sixth property, scalar multiplication. Scalar multiplication. Now take any alpha belongs to field. Whenever multiply this alpha Pn, this will get alpha a0, alpha a1, alpha a2, and alpha an. A0 is real number, alpha is real number. Alpha a0 is real number. Alpha a1 also real number. This coefficient all are real numbers. This coefficient suppose alpha Pn. Alpha Pn means we get alpha a1, a0 plus alpha a1x and so on, alpha an xn. This is a coefficient all real number. That means it's a real polynomial. It belongs to vector space. Now you can check 1 dot Pn is same as Pn, and you can check distribution laws. Satisfied. That means this polynomial set of all polynomials whose degree less than or equal to 10 is a vector space. You can check all conditions. Just I give an idea. Try this one with yourself. I will see another example. The set of all m by n matrices over the real field under the usual matrix addition and scalar multiplication of matrices is a vector space. This is set of all matrices, m by n matrices. The vector space V equal to the rate m. That's a set of all m by n matrices. The notation V equal to n. Nn means square matrices. So we write mn. This is set of all square matrices. Mn means m by n matrices. Space. Real field. That means field is real. Usual matrix addition and scalar multiplication of vectors. Suppose A comma B belongs to vector space. Vector space is the set of all m by n matrices. That means A is equal to some take Aij. We are writing m by n matrix. And B equals also some Bij. Now we have to check all matrices, all properties. Closure property. If write A plus B, what is A plus B equal to? Aij plus Bij. So where A's and B's belongs to real numbers. This whose elements of matrices, real matrices. whose elements are real. So these are real numbers. We are this one correct. Aij plus Aij. A plus B equal to Aij plus B. It belongs to vector space. It belongs to vector space. That means it satisfies closure property. Similarly, you can check associative property. Already you know this matrix addition is satisfied associative property. And identity. Zero matrix is there. Zero matrix. This is zero M by N matrix. Identity. Inverse. Negative matrix. A is A plus minus A. Minus A is the negative of A. Additive inverse is there. And matrix addition satisfies completive property. It's multiplication is not satisfied completive property, but addition is satisfied completive property. You know, right? Means you can write A plus B same as the B plus A. You can check scalar multiplication. Suppose A is this one. Alpha dot A. That means alpha into Aij. Yeah, Aij is a real number, alpha is a real number. This again belongs to vector space. And 1 dot A is again same itself. And it's also distribution laws. You can check it. This is also vector space. Now take A plus B, A comma B belongs to means A is a B. So you take C belongs to vector space. Take C equal to some Cij. Again it's M by N matrix. M by N matrix. Now we'll see another example. Now try these examples. You can check all 9 conditions. The set of all real and continuous functions. Real continuous functions. Set of all continuous functions in the interval 0, 1 over 0, 1 denoted by the set of all continuous functions. We write this one C over 0, 1. Its notation means this notation represents set of all continuous functions over 0, 1 interval. Over the real field, that field is real numbers with vector addition and scalar multiplication. That vector addition and scalar multiplication defined like this one. F plus j of x is this one. The scalar multiplication is this one. So you have to prove that is a vector space. Two vectors. It's given closed property. Vector, addition closed and scalar is closed property. Already you know sum of continuous function is continuous function. Suppose any two continuous function against continuous function, it's closed property. Then take associative property. Take f plus g plus h. The same as you can write f plus g plus h of x. You can check it. This one. Associative property. Completive property. This one f plus g of x you can write same as g plus of f of x. The sum of continuous function f of x plus g of x same as the g of x plus f of x. Zero function. 0 of x. It's a continuous function. Null function. Zero function is a continuous function. This is additive identity. And if function is there, the negative function also there. If f of x, this minus f of x also in a vector space. If you take f of x, right, this one, f plus minus f of x, we'll get this zero function. The minus f is the additive inverse. It's also a commutative property. And it's scalar multiplication. Alpha f of x is alpha f of x. Alpha is some number. F of x is a function. Again, it is a vector space. This one. And it's also a distribution laws. All this one. You can check this one. 9 conditions. This is the one. Now null space. Or you can say zero vector space. What is the null space or zero vector space? The vector space having only one zero vector. The vector space having only one zero vector is called the null space or zero vector space. Then we write this one. The null space or zero vector space, we write this one. Only zero vector. Write only zero vector. If I write this one, it's a null space. That means it's a vector. It's a vector space. It's also all 9 conditions. Now, some theorems. Simple. Prove that any vector space V over any field F, any vector space or any field, for the condition alpha dot 0 equal to 0 for all alpha belongs to F, alpha dot U equal to 0. Yeah, I'm representing this 0 thick bold 0. It's a vector. Ordinary 0 is the scalar. U belongs to V. If you write element in V means this is a vector. Element in F means it's a scalar. Minus 1 dot U is minus U. This one. The proof is simple. Take first one. Alpha dot 0. We have to prove alpha dot 0 is 0. Alpha dot 0 vector. This one can write alpha dot 0 vector plus 0 vector. Now distribution laws. Alpha dot 0 plus alpha dot distribution law. Correct. It's a distribution law. Distribution property or law. Distribution property. And now alpha dot 0 plus 0 0 vector. The same as alpha dot. When you are adding 0, we get alpha dot 0. This implies alpha dot 0 plus 0 vector equal alpha dot 0. From this one, alpha dot 0 equal we get alpha dot 0 plus alpha dot 0. By cancellation laws, this is by cancellation, this is cancel left cancellation. That means 0 bar equal to alpha dot 0. Or you can write cancellation. Here you can take 0 plus alpha dot 0, you get alpha dot 0. In that case, you get right cancellation law. Here left cancellation by cancellation laws. Yeah, therefore this one. Yeah, there. Okay. Okay, this is the first, okay, right, first one. This is the first one. Second one. Third one. 0. Yeah, therefore alpha dot 0 vector equal to 0 vector. Now second one, 0 dot equal to, sorry, this 0 vector. 0 dot equal to 0 vector for all u belongs to V. See now take 0 dot u. This equal to current 0 plus 0 dot u. Now distribution law 0 dot u. This one distribution, the vector distribution on scalar. And now we are using your left cancellation. You can use your right cancellation, means you can write 0 vector plus 0 dot u is equal to 0 dot u. Simplies 0 vector plus 0 dot u. Or the 0 dot u equal to 0 dot u plus 0 dot u. Now right cancellation law is equal to 0 vector equal to 0 dot cancellation. Therefore 0 dot equal to 0 vector for all u belongs to V. For any vector, we multiply with scalar, again we get vector. Here multiply 0 vector with scalar, get 0 vector. Any multiply with 0 with any vector, we get 0 vector. Okay. Okay, third one. Third one is minus 1 dot u equal to minus u. Or the minus 1 dot u. You can write 0 dot u equal to, this one can write 1 minus 1 dot u. The same as 1 dot u plus minus 1 dot u. What the 1 dot u is? Same u plus minus 1 dot u. And now u plus 0 dot u equal to, or the u plus 0 dot u equal to u plus 0 dot u. 0 dot u equal to u plus 0 dot u equal to u plus Okay, right. Minus u plus 0 dot u. Minus u plus u. Okay. Okay, now minus u plus 0 dot u. This equal to minus u plus 0 dot u equal to u plus minus 1 dot u. Minus 1 dot u. This implies minus u plus 0 dot u. Okay, right. One more thing. What is 0 dot u equal to? 0 dot u equal to 0 vector equal to minus u plus u. Additive minus u is the additive inverse of u. That is again 0 vector plus minus 1 dot u. This equal to minus u plus 0 vector is minus u equal to 0 vector into minus 1 of u minus 1 dot u. Therefore, minus 1 dot of u equal to minus u. For all u belongs to this the one. So this is the third condition. Now let's see another example. Examine whether or not the following will make the vector space over F under given operations. Is it a vector space over a field given one? We are given two. V is equal to Rn. Rn space. F is a field or two elements in V. That is V means R2. Alpha belongs to F. Alpha is the R. Define vector addition is like A1 comma A2 equal B1 B2. This one. Scalar multiplication this one. Now you have to. It's suppose it's not a vector space given any counter condition. Now observe here alpha dot A1 A2. Alpha dot A1 A2. Generally, what the scalar multiplication is equal to alpha A1 comma alpha A2. Alpha A1 comma A2. This is scalar multiplication. But this is not equal to A1 comma 0. That means not satisfied scalar multiplication. Yeah, therefore, this is calculate. Therefore, R2 over R is not a vector space. Vector space. Not only this one, you can give any condition, or you can give another condition. This is called, or you can observe here this 1 dot A1 A2. But 1 dot A1 A2 must be A1 A2. But by using this condition, if you take alpha is 1, we get A1 0. It's not equal to A1 A2. That's why it's not another condition. Sixth condition also. This is seventh condition. You can give any one, but it's not a vector space. Now observe second one. Second one. In the above problem, if no change in the addition operation, this addition operation there is no change. Addition operation satisfies all conditions. Five conditions. Only problem with scalar multiplication. Already we know we are checking first example like this one, this problem only. This definition only, this addition property. That's why it starts for this one. We checked in Rn space, but in only R2 space. So now addition, but it's different as this one. Same thing, alpha A1 A2. This equal to generally scalar multiplication is alpha A1 alpha A1 comma alpha A2. But it's not equal to alpha A1 comma A2. But it's given definition is alpha A1 comma A2 is alpha A1 A2. But we know scalar multiplication is like this one. Therefore, not satisfied scalar multiplication. Multiplication. Therefore, R2 over R is not a vector space. This one. Let's see another example. So examine whether or not the following will make the vector space over F. Same thing. Given vector addition is this one. A1, vector addition A1 plus 2B1, comma A2 plus 3B2. Scalar multiplication is alpha A1, comma A2 is alpha. This scalar multiplication satisfies the condition. You can check this one. Now observe here this first one. Solution. Now observe first one. Now A1, comma A2 plus B1, B2. Are given A1 plus 2B1, A2 plus B2. So this vector addition must be satisfy all conditions, 5 conditions. Okay, it must be satisfied commutative property, associative property, or you check associative property or commutative. Now I'm checking commutative property. You can check it B1, B2 plus A1, B2. It must be equal. What will get B1, B2 plus A1, A2? A1, A2. A1, first element A1, and is the first element is B1. B1 plus 2B1. This is second 2B1. In B1 place is A1. It's a 2A1. Next, A2. A2 plus is B2 is there. B2 plus 3 A2. These are not equal. See now observe here, these are not equal. B2 not equal to B1 plus 2A1, B2 plus 3A2. Or you can take any by numbers also. Suppose take 1, comma 2, 3, comma 4. Whatever you take number, but it's not equal. Commutative properties, commutative property not satisfied. Therefore, R square over R not a vector space. Or you can give any other reason. It's enough to give one counter property. Or you can take by example also, by numbering. Suppose you take A1, A2 are real numbers. You can take 1, comma 2 and 2, comma 0 or whatever. 2, comma 0. Simply you can take 1, comma 2, 2, comma 0. Now take, now check this commutative property. It's not satisfied. Not get same property. Not only commutative, you can check associative property also. It's not hold. Maybe associative property hold, but commutative is not. So it is, you can check it this one. If at least one property is not satisfied, then the set is not a vector space. Now we'll see another example. Second one. Let V be the set of all real polynomials of degree greater than or equal to 2 over the real field under standard addition and scalar multiplication of polynomial. Yeah. So degree greater. Suppose take example. Take it's more than 2 degree. Take P of x equal to degree more than 2. Suppose I'm taking 2x square plus 3x. Suppose it's a degree 2 more than, and P of x equal to I'm taken minus 2x square plus 5x. Now take vector addition. P of x plus P of x. Now what the P of x plus Q of x equal to 2x square plus 3x minus 2x square plus 5x. 2x square minus 2x square 0. This is 3x plus 5x is 8x. But whatever this degree is 1. It's not more than 2. This is not degree. But the degree of P of x plus Q of x is not greater than or equal to 2. Therefore, not a, it is the, therefore V is not a vector space. Not a vector space. You can give any counter example. Suppose it's not a vector space. For example, now remember this polynomial. Set of all polynomials whose degree less than or equal to n. Now you can remember set of all polynomials whose degree less than or equal to n or less than n. It's a vector space. Suppose set of all polynomials whose degree greater than or equal to n or equal to n or strictly n is not a vector space. Suppose equal to n. Suppose a set of all polynomials whose degree 3. Suppose whose degree 3. It's not a vector space. Whose degree 3. Suppose I have taken p of x equal to set of all polynomials, whose degree whose degree 3, exactly 3. Suppose. So I'm taking p of x equal to x cube plus 3x square plus 5x. So, whose degree of polynomial is 3. So I'm taking q of x equal to minus x cube plus 2x square. Okay, 2x. Okay, 2x square plus 5. Okay. But check. It's a vector space, but it must be also a vector addition. The addition property. When you are adding addition, we are adding this two polynomials. What we'll get? 3 plus 2, 5x square plus 5x plus 5. What is the degree of this one? See, the vector space degree 3. Every polynomial degree 3. This is suppose in a vector space V. Is it not a vector space? Okay, 3. But this is degree of this one is 2. But it's not belongs to V. Suppose V is set of all polynomials whose degree 3. But it's a degree of polynomial is 2. This is not belongs to V. That means it's not closed. Not closed means it's not such a vector addition. Therefore, V is not a vector space. Now remember this for polynomial, set of all polynomials less than or equal to n or strictly n is always a vector space. So more than n or equal exactly some n, like this one, exactly set of polynomials whose degree 3. This is not a vector space, like this one. Okay. And now now I go through this lecture. Now try those problems. Just I given some idea. Try the problems. If you have any doubts, we'll discuss in doubt session. Now I stop here. Next class we'll discuss subspaces. Okay, thank you.